In Part 15, some of the terms that were used throughout the series have been clarified. That allows for further discussion regarding titration. In this presentation, Part 16, the focus will be on a very important subject that relates to achieving an accurate titration. It is the subject of glassware calibration. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. All glassware has a certain amount of uncertainty. They are not 100% accurate. The degree of uncertainty stems from temperature and elasticity. As temperature increases, the glass containers will expand to some degree. As the temperature decreases, the containers will also contract in size. Distilled water will also expand and contract in volume. Albeit very small over time, the accuracy of the analysis may be affected. In addition to, manufacturing processes will not produce an exact copy of each container. There will be some slight differences. Although microscopic, all will contribute to systematic errors. These are all unavoidable. Errors, however, can be minimized by performing calibration techniques. In the factory, the glassware is calibrated at standard conditions. The test chambers are environmentally controlled for a temperature of 20 degrees centigrade at 1 atm. Now 1 atm is equal to 14.6959 psi, or a standard atmospheric pressure of 0.999996681 atm, to be more precise. Well, 1 atm is close enough. Some, if not most, will have their tolerances etched into the glass. The slightest variation from any of the conditions produces a systematic error. Some of the general tolerances etched into the glassware are shown, where a Class A 10 mm pipette would have a tolerance of plus or minus 0.02 milliliters, or a 90.8% accuracy. For a 250 ml graduated cylinder, the tolerance may be plus or minus 10 mils. These would be considered tolerable. If the calculated calibration volume is within these limits, the measured volume would be considered as being accurate. However, if more precise results are required, that is, greater than 95%, a calibration must be performed, and the calculated volume would be used. Now, before moving forward, there are two tables that can be used for the procedure of calibrating glassware. I suggest searching and downloading a free copy of these tables. The first is a corrected volume table. The second table is the water density table that lists the density of distilled water, that is pure water, at different temperatures. Volumetric glassware is always calibrated using accurately weighed deliveries of water. The water that is placed into a container is commonly added by a burette. The reason for the weighing of the distilled water comes from the fact that volumetric measurements are not as accurate as the weight measurements of mass. Any distilled water should be boiled first and cooled to room temperature. This releases any unwanted gas that may have built up in the solution, maybe due to atmospheric contamination. It is known that 1 liter of water is considered as the volume of water that equals 1,000 milliliters, or 1,000.025 cubic centimeters, and has a mass weight of 1,000 grams at 4 degrees centigrade. This works out to be 1 gram per milliliter or cubic centimeter. The correction table is based on the equation shown where W1 is the corrected mass of the object, W2 is the mass of the standard masses used, and the D object is the density of the object, where dWTS is the density of the masses, and d air is the density of the air that is displaced by the masses and the object. Using the tables is far less time consuming. Using the correction table as a quick example, if 24.976 grams of distilled water was added to a container at room temperature of 25 degrees centigrade, from the table the correction factor is shown to be 1.0040. Now multiplying the correction factor by the weight of the water gives us a correct volume of 25.08 milliliters. Now using the correction value to correct the volume to 20 degrees centigrade, the factor given for the 20 degrees centigrade volume is 1.0037. Therefore, multiplying this value by the mass weight of the water at 20 degrees centigrade, the volume would be 25.07 milliliters. Now using the density table, the true value of the volumetric flask can be determined. As well, the tolerance can be compared to the stated value etched on the bottle. Let's say, for example, we have a 1,000 liter flask having a tolerance of plus or minus 5.0 mils at 20 degrees centigrade. Well, the flask is filled to the meniscus and carefully weighed. The room temperature is 18 degrees centigrade and the weight of the water was 997.55 grams. Okay, now the table shows the weight of 998.29 kilograms per liter at 20 degrees centigrade. Well, the true volume is calculated by multiplying the measured weight against the 1,000 mils divided by the 998.29 grams. This equates to a true volume of 999.26 milliliters at 20 degrees centigrade. When the meniscus was etched in at the 1,000 mil mark, 1,000 mils minus the 999.26 mils gives us a difference of 0.74 mils. Well, the 0.74 mils is well within the stated plus minus 5.0 mils. Therefore, the filled volume of 1,000 milliliters could be considered as quite accurate. Laboratory glassware must be clean, totally clean. This avoids any possibility of contamination. Organic material in the air is the biggest factor. It will adhere to almost all surfaces, and that includes laboratory glassware. Clean, in this context, is mandatory, especially for calibration. A clean piece of glassware will not have any residue on the glass surface after draining. There will be no beading, and the fluid will be smoothly draining, leaving no residue or remaining fluid. There are many ways that glassware can be cleaned, by hand or by machine. The solvents used to clean glassware vary. A chromic acid solution may be used. It is a solution made by dissolving potassium dichromate in a solution of sulfuric acid. However, this solution is quite toxic and corrosive. It may require special disposal. Other solvents used are other acids. It all depends on the nature of the dirt deposits. Basic solvents and/or organic solvents may also be used. There are many detergents on the market that are designed for industrial use. One such solvent is T-Pol, which is commonly available and used in many commercial laboratories. Volumetric flasks, graduated cylinders, and beakers are the easiest to calibrate. There are 3 steps that are used to calibrate these containers. Calibrating a volumetric flask uses the same procedure as for calibrating the other 2. The first is to weigh a clean dry flask, then record the weight. The flask is then filled to the meniscus line, which would be the graduated volume mark on the flask. For beakers and cylinders, it would be the full mark. The weight is measured and the temperature is recorded. The difference in the 2 recorded weights will be the weight of the distilled water. This weight is also recorded. The appropriate density value from a density table is chosen, or the correction factor from a correction table is used to determine the accurate volume of the solution. Using the difference marked on the container versus the actual, it can be used to compare the tolerance value in milliliters. For example, the determined weight of water at 18 degrees centigrade is 998.39 grams. From the density table, the listed value at 20 degrees centigrade is 998.29 grams per liter. Using the previous formula, the 998.30 grams multiplied by 1,000 milliliters divided by the 998.29 grams per liter will equal 1,000.01 milliliters. 1,000.01 milliliters would be the actual volume in the volumetric flask. Since the tolerance is 0.08 milliliters, plus or minus, the 0.01 milliliters shows that the 0.01 is within the volumetric flask's tolerance specification, and the volume marked by the meniscus could be used and considered as accurate. If not, then the calculated volume would have to be used, and the graduated marks are out of spec. To be more accurate, this procedure should be repeated at least 3 times, and the average volume taken from the 3 calculations would be the correct volume. There are mainly 2 types of pipettes, transfer and graduated. Transfer pipettes are either preset or have variable presets that are selective. Unlike beakers and containers, such as volumetric flasks, pipettes do have some variables associated with them, such as drain time and drainage angles. Beading on the inner surface, depending on the type of pipette, may be visual, or it may not, such as the transfer pipette shown. There are other variables, such as temperature of solution, meniscus levels, and calibration procedures, such as touching the last drop. And then there is rinsing and calibration. To start, the pipette, as with glassware, must be clean. The pipette must be thoroughly rinsed with distilled water, then filled above its mark. The water temperature must be recorded. Any water must be wiped away from the tip. The pipette is then held vertically with the tip touching a container to carefully adjust the volume to the meniscus mark. Touching the container removes any adhering liquid from the tip of the pipette. Using a second clean, dry, pre-weighed container, holding the pipette at a slight angle, while touching the tip against the container wall, the contents is drained. The drain time is recorded. To ensure total draining, the pipette is held for another 15 seconds. This ensures that the pipette has been completely drained. The weight of the drained liquid is recorded, along with the draining time, less the 15-second wait time. Using the density of the water table, at the recorded temperature, calculate the true volume as previously shown. Verify the obtained values with the manufacturer's specification in regards to tolerance and minimum delivery time. This procedure is repeated at least 3 times, and the average, that is, the mean results, are used as the calibrated value. Burette calibration is a little more complex and time-consuming. Burettes are used when accurate and precise determinations are required. Burettes are much more accurate than graduated cylinders and beakers. As always, weight is used for calibrations, as was already shown and discussed. For burettes, in most cases, buoyancy calculations can be ignored. However, for more precise determinations, they must be included. The next few slides will demonstrate the calibration and the recording of the calibration. To start, there will be some items that are required, besides a burette, a clamp, and a stand. The laboratory scale that you will use must first be calibrated with a calibration weight that is recommended by the laboratory scale's manufacturer. Now, these weights are considered to be extremely accurate in weight. It will also be used to determine the weight's density. A graduated cylinder of suitable size, large enough to contain the calibration weight, and a couple of beakers, graph paper to record the findings, and if you have a computer with Microsoft Excel or equivalent, would also be a nice tool to use. The first step is to determine the density of the calibration weight used to calibrate the lab scale. Adding enough distilled water to a clean graduated cylinder to completely cover the calibration weight when added is recorded. The weight is then added to displace the water in the graduated cylinder and the volume recorded. The difference between the two recorded volume measurements is the volume of water displaced. The density, either written as lowercase p or d, is the mass of the calibration weight divided by the amount of liquid displaced, and recorded as grams per cubic centimeter. Since 1 millimeter is equal to 1 cubic centimeter, as shown, the hypothetical volume of the object is 25 cubic centimeters. If the weight was 50 grams, then the 50 grams divided by the volume of 25 cubic centimeters, the density would be 2 grams per cubic centimeter. The weight of the calibration scale and its density must be recorded. To begin the actual sequence, ensuring that the burette is absolutely clean and dry, a clean dry weighing bottle or beaker is weighed. The weight is recorded and set aside for the calibration sequence. Distilled water, enough to completely fill the burette, is placed into a second beaker. It is left standing for about 5 to 10 minutes to reach room temperature. Temperature is then measured and recorded. Once the temperature is recorded, the burette is then filled to a point well beyond the 0 mil or 0 centimeter cubed mark. A second beaker or suitable container is used to carefully dispense the liquid, dropwise, until it reaches the 0 mark on the burette. The tip of the burette is touched against the side of the container to remove the last drop adhering and discarded. The previously weighed beaker or weighing bottle is now used. The burette is carefully drained, dropwise, into the container to the 5 mil mark on the burette. The tip of the burette is touched to the wall of the beaker or weighing bottle to remove that last drop, and the container is weighed. The volume weight is recorded. The weight of the solution in the container would be the total weight of the container and the solution minus the weight of the container. Now this process is repeated until the burette is completely emptied to its rated mark, example 250 mil or 100 mil, etc. Also note that the calculation for each volume segment must be subtracted from the previous. The first 5 mils is simple, as that was the only weight considered, minus the weight of the tared container. However, the container with the solution will have additional solution added for each 5 mil segment. The weight of the second measurement would be subtracted from the one before it. Then the tare weight of the container is subtracted, giving us the final weight of that segment, or for that segment. This is the same process for the remaining segments. Now once all segments are weighed and weights recorded, using the correction equation shown and previously used, and the density of the liquid water table at a given temperature, the correct volume of each segment must be calculated and recorded. These values are used to construct the calibration table for the burette. Note, in most cases these values can be used for titration, as the air buoyancy factor is so small that the calculation can be ignored. However, if precision, accuracy is required, this will be shown in the next few slides. Buoyancy can skew accuracy and precision to some degree. When a boat floats in water, the weight and density of the body of water outweighs the weight and the density of the boat. Since the weight and the density of the boat is much less, the boat floats. When the density and the weight of a submarine, for example, is almost equal to the weight and the density of the surrounding water, it will partially float, it will suspend itself within the body of water surrounding it. Now, air is similar to water. It surrounds everything. As a beaker or other container is placed on top of a laboratory scale, the air on top of the pan is displaced. There will always be some atmosphere, albeit microscopically thin, still adds weight. That is added to the weight of the object that is placed upon the pan. In essence, the container actually floats on top of that extremely thin volume of air, similar to the submarine. That weight must be accounted for. The equation shown accounts for the amount of air that is being weighed in conjunction with the mass applied, which would be the beaker or other container. Now, this is the easiest way to explain it. WV is the true weight of the dispensed volume, whereas WA is the measured weight of the dispensed volume less the weight of the container. Now, DO is the density of the water at a given temperature taken from the density of water table, and DW is the density of the calibration weight used to calibrate the lab scale. The D air is the density of air at 1 atm or atmospheric pressure and measured temperature. This is taken from the density of air table. If accuracy is of most concern, then this equation is used. Now, I prefer this equation for calibrating laboratory glassware. Using a hypothetical scenario, let's try to put it together. The steel calibration weight used to calibrate our scale was determined to be 8.40 grams per cubic centimeter. 100 mils of distilled water was set aside, and the temperature was measured to be 20 degrees centigrade. The water density table used listed the density at 20 degrees centigrade to be 998.29 kilograms per meter cubed. This equates to 0.99829 grams per cubic centimeter. The air density table listed the air density at 1 atm or atmosphere and 20 degrees centigrade as being 0.001204 grams per cubic centimeter. A 250 ml beaker weighed on the lab scale displayed 106.00 grams. 3 calibration procedures were conducted, and the average of the 3 measurements were recorded as shown. The equations used for this hypothetical calibration of a 50 ml burette are also shown. VW is the buoyancy corrected weight of the solution. WA is the measured weight that was dispensed, minus the beaker weight. This was calculated as shown in the previous 2 slides. The density of the water listed in the density of water table at the 20 degrees centigrade is 998.29 kilograms per cubic meter, which is the same as the 0.99829 grams per cubic centimeter. Well, the final true volumes of each 5 ml dispensed weighings, a calibration graph, sometimes incorrectly stated as a calibration curve, can now be plotted. To make the calculations less tedious, an Excel spreadsheet is used. An open source spreadsheet such as LibreOffice, which can be downloaded for free, can also be used. Based on the hypothetical scenario and values from the previous slide, and incorporating the use of an Excel spreadsheet and a graphing application, this graph shown is the result. Excel does not do a great job on the graphing styles, such as the one shown. The blue line in the center of the graph shows the number of milliliters that the burette contained at 20 degrees centigrade. Each vertical line represents the 5 milliliter segments, which was dispensed. The red dots are the measured and calculated true volume of each lot of 5 milliliters up to the 50 milliliter mark. The red line that connects the dots is used to extrapolate the estimated true value, or that is volume, dispensed from the burette. The yellow line is an example of how that is achieved. If 38 milliliters was dispensed, At that point, the red line pivots downward, drawing a straight line vertically to a point where the line intersects with the red line, then extending that horizontally to the y-axis. The variation in milliliters is roughly 0.057 milliliters. Now 38.00 minus the 0.57 gives an estimated true volume of 37.943 milliliters. At 43 milliliters, the red dot is positive on the graph. By drawing the line vertically to the red line, then across, the variance is roughly 0.075 milliliters. Therefore, the estimated true value would be 43.0575 milliliters. If accuracy to this degree was not required, then it would be safe to say that the volume, or 43.00 plus minus 0.17%, would be used as the volume dispensed. It would also be enough to state that the estimated volume falls well within the rated specification of the burette, and that there are no specific environmental effects associated with the burette's matrix. This process of evaluation and glassware calibration can be used for all glassware, and the correction table would be used to correct the volume estimated at different temperatures. Well, this concludes part 16 of the series on classical chemical assay for small-scale miners, prospectors, and hobbyists. In this presentation, the calibration of glassware has been introduced, along with some basic calculations and the tables that can be searched and downloaded for use. The use of a spreadsheet was mentioned, along with the accompanying graphing software. Open source graphing software can be found by a Google search and downloaded for free. These are usually open source. LibreOffice is an open source suite which can also be downloaded for free if you do not have Microsoft Excel. The use of a calibration graph was shown as being useful for estimating the volumes of your glassware instead of calculating each dispensement. I hope that this presentation entices you to view part 17 when it is published. If you found some of this presentation or know of someone who would benefit from this presentation, please give it a like and a share and maybe a subscribe. It's my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.